this time we need to prove it. So that formula is correct. After that, then we need to find a way to discover it. Yeah. All right. So part E.1, verify Fibonacci formula special cases. Yeah. To verify it, at the beginning, we just verify the special cases. So that will be easy. Yeah. Later, we will look at the general case. Yeah. All right. The problem, our computing problem number 10. Yeah. It is just a recurrence relation, a very simple recurrence relation. Yeah. And here, the formula, so here, let's bypass the formula discovery step, because that step quite complicated. So let us bypass that step first. Yeah. Someone gave us this formula. Now, f sub n equals 1 over root 5 times big parenthesis, inside the parenthesis, phi to the nth. Phi, that is the golden ratio. Yeah. So remember last time, we find the golden ratio, its value is 1 plus root 5 over 2. Yeah. All right, so then in the big parenthesis, phi to the n minus negative 1 to the nth over phi to the nth. Okay. So this expression, quite unusual. We know Fibonacci number. So remember last time I gave you the approximate value 1.618, and many digits after that. Yeah. Infinite. Yeah. Actually infinite number. And there is no cycle. Yeah. So this kind of number we call it irrational number. Not rational. So rational number, if it's infinite, you can discover some cycle repeated many, many times. Yeah. But here it is infinite number of digits without any cycle. All right. Yeah. So that's the irrational number. But this irrational number, first you raise to nth power, then minus negative 1 to the nth over phi to the nth, then the whole thing divided by root 5, it becomes an integer. That integer is the Fibonacci number. Yeah. Yeah. So something, if you do not prove it in some special way, it is very hard to believe it, right? So we need to find a way, convincing way to tell us it is correct. So let us do this verification work. Yeah. When we start, we like to verify the simplest cases. Yeah. All right. Step 1, let's look at the when n equals 0. Let's plug in. When n equals 0, capital F0, the right-hand side, we plug in phi to the 0, it's 1, right? Yeah. And negative 1 to the 0, also 1. So 1 here, 1 over 1, 1 minus 1, that's 0. So the right-hand side, 0 over root 5, also 0. That's just the same as our base case. F0 equals 0. That's correct. Okay, so the step 1, that is the easiest verification step. Now step 2, when n equals 1. Let's plug in. Is it correct? We need to do some computation here. All right, yeah. Let us use the golden ratio number there. 1 plus 5 over 2, because negative 1 to the 1, it's also negative. Negative becomes positive. Yeah. Then reciprocal, 1 over phi reciprocal, so 2 over 1 plus root 5. Yeah. But here we need to convert it, yeah, because 1 plus root 5 at the denominator, it is not very convenient in our calculation. So we like to change its form. We do transformation on it. How to do it? You know, I believe most of you know how to do it. Yeah. So here I just, you know, write the step a little more. Yeah. We call the rationalization. 1 plus root 5. Can you multiply? Oh, sorry. Yeah. 1 plus root 5. Here there is a conjugate concept. 1 minus root 5, 1 plus, we multiply 1 minus root 5. We call its conjugate of the root 1 plus root 5. Yeah, because the same number over itself, it is 1, so we do not change its value, right? Yeah, do simplification, the numerator 1 minus 5, right? Yeah, a, remember here we use the formula a plus b times a minus b equals a squared minus b squared. Okay, so here we apply that formula here at the denominator. So it is 1 minus the root minus 5. Okay, square of root 5, 1 minus 5. The numerator 2 times 1 minus root 5. Okay, then after simplification, 2 over negative 4, 1 minus root 5, right? Yeah, it is a negative, but 1 minus root 5 also negative. So let us change the sign. 1 over 2, use root 5 minus 1 becomes positive. Okay, so that is the form. Yeah. So now we do addition between these two fractions because they have the same denominator 2, and for the numerator, minus 1, 1 cancel out, 2 root 5, right? 2 root 5. Yeah. But you cancel out the 2 at the denominator. So root 5 at the numerator, and this one cancel out with that root 5. So you get 1. Yeah. You get 1. Yeah. Yeah. That's step 2. Yeah. Hope you can see it easily. Yeah. So here you can see we get the F1 equals 1 for our second base case. Yeah. All right. Yeah. Is it enough? Yeah. Yeah. For mathematical induction, it is enough. Yeah. Here we plan to do verification. We plan to use the mathematical induction. Mathematical induction. Now, let me recall mathematical induction a little bit. Step 1, verify the base cases. We just did it. There are 2 base cases. We verified it is correct. Step 2, make induction assumption. All right. And 3, because it's hard to use simple words to represent it. Let me just say advancing our assumption by 1. Okay, because our assumption, we use a parameter k. Advancing our assumption on k by 1. More specifically, All right, so we will follow. So that means after the base case verification, we do not need to do more cases verification. That's enough. But for our practice here, because doing verification, you need some algebra technique to handle the computation. And I feel for many of you, so probably you're not very strong in this kind of algebra. So I like to do a little more practice. So let us do a few more cases verification. So we just do it, that part, this part as a practice. So case number 3. So let's do one more verification. This time, let's verify F2. Because F2, we know its value, it is also 1, right? 0 plus 1, so its value should be 1, but now we want to check if the right-hand side expression also gives us value 1. So let us use the value. But this time, the golden ratio, the reciprocal part, because -1 squared, that's 1. So we keep this minus sign. And the second term, because we did the, rationalization before. So let us just use that number, replace 1 over phi squared directly. Okay, so so this time we need to do expansion. So when we do expansion, we apply the formula, another formula. So I hope everyone is familiar with it. A plus minus b squared. A plus b squared, A minus b squared. Let me write these two together. A squared plus minus 2ab plus b squared. Okay, so we apply this formula. So we get these two expansion expressions. The same denominator for the numerator part, you can see 2 root 5. No cancellation, because look at that. minus sign, it becomes plus sign, right? Yeah, but 5 cancel out. Okay, yeah. 1 cancel out because this minus sign here. All right. So 2 root 5 plus another 2 root 5, 4 root 5. 4 cancel out the denominator 4. So we get root 5, right? Numerator root 5. Root 5, then external 1 over root 5. Another cancellation for root 5. So you get the answer 1. Yeah. That's also correct. We just verify F2 equals 1. Yeah. So this step number 3 is also correct. Yeah. All right. Yeah. So we did 3 simplest cases verification. Yeah. All right. Next, I like to do another case verification. Yes, although it's not necessary, but still we like to do one more practice verification. Okay, yeah. So this time, step number 4, we try to verify F3. Yeah, F3. Yeah, because F3 equals F1 plus F2. F1 equals 1, F2 equals 1. So F3 should be, should be 2. All right, let's take a look. If the right-hand side expression gives us value 2. All right, so let's do it. Yeah. But here, you can see the degree phi, it's 3, becomes relatively high, right? Relatively high, okay, yeah. Although we can use the usual way, the old way, the way we use in the previous step, yeah. We can use that same way to do verification, yeah. So that is, so more specifically, that is 1 plus root 5 over 2 cube plus, right? Because -1 to the cube, that's also -1, negative, negative, positive. So, and the root 5 minus 1 over 2 cube. Although you can do expansion on these two, when you do, you can use the a plus minus b cube formula, right? Yeah, so let me write cube formula. A cube plus minus 3a squared b plus 3ab squared plus minus b cubed. Okay, yeah, a little more complicated, but if you work slowly, carefully, then you can get the correct answer. Yeah, but here I want to use a different way. Okay, so I do not go, that usual way. Yeah, I try to find a smart way to do it. Yeah. All right. What is that smart way? Yeah. So here, I like to reduce the degree of phi cube. How to reduce it? We know this phi is the golden ratio. It has some very special properties. So we just apply the special properties of phi. Yeah. So let me start with the properties of golden ratio number. Now, there are two properties. The first one, 1 equals phi squared minus phi. The second property, phi squared equals phi plus 1. How do we get it? Why we have these two properties? You may ask me this question. Yeah. The answer is very simple. The answer is very simple because let's recall, how did we find the value of phi? Because we solve a quadratic equation by the quadratic formula. What is that quadratic equation? The original equation for the phi, that is x squared minus x minus 1 equals 0. And we can call phi is a root of this quadratic equation. Yeah. The root means if we plug in phi, the equality should hold. So we should have this identity, equality or identity, okay? This equality, we know it's correct, but we can write in these two equivalent form, okay? Yeah. So you can see if you move 1 from minus 1 term from left-hand side to right-hand side, you get the first property. Then if you move minus phi, minus 1, both from left-hand side to right-hand side, you get second property. Okay, so equivalent expressions. Yeah. But if we use these two forms, yeah, so then it's more convenient in our computation. Okay, all right, so now let's start using these two properties to do the step 4 verification. Yeah. When we start, let us try to reduce the degree of phi cube by using these two properties. Yeah. First, let us write phi cube as phi times phi squared. Okay, so why we split? Because we want to use one of the properties. After the split, you have that phi squared expression. That means we can apply property number 2. Okay, so it becomes phi times phi plus 1. All right, so let us multiply through, so we get phi squared plus phi, but this phi squared, we can apply our second property another time. Yeah, so that is replace phi squared by phi plus 1. So we get 2 phi plus 1 for phi cube. Yeah. This time, the good thing is the degree becomes lower. The degree from original expression, that's 3. After we do transformation, we get the degree becomes 1 here, right? 2 phi, degree 1, 2 phi plus 1. So degree much lower. The lower, the easier in our calculation. Yeah. All right, so that's the phi cube. But there is another term, 1 over phi cube. Yeah, this time it's a fractional form, a little harder than, phi cube form. Yeah. So this time we want to do transformation to get a more friendly form. All right. So how to do it? Yeah. 1 at the numerator, But the 1, we can replace it by our property number 1, phi squared minus phi. Yeah. Why we replace 1 by phi squared minus phi? Because we can do cancellation. Cancellation, the common factor cancellation between numerator and the denominator. They have a common factor phi. Okay, yeah. After cancellation, the numerator becomes phi minus 1, denominator becomes phi squared. Okay, yeah, all right. So this time you can see when we do the transformation, we do the equivalent form change on the numerator, not denominator. Yeah, so why? The denominator, we keep the phi to some number, that form, the power form. Yeah. Why? Because that power form is a very friendly form for cancellation. For cancellation, for phi cancellation. Yeah. So we keep that power form. Yeah. All right. Because you should not replace phi squared as a denominator by phi plus 1. Because if you use phi plus 1, it won't be a power form, right? Then it's not friendly for phi cancellation. Yeah. So we keep that power form at a denominator for further cancellation. Yeah. All right. And the numerator, you see 1 another time. Can you replace that 1 by phi squared minus phi again? Yeah. So we can do that substitution another time. After simplification, we get 2 phi minus phi squared at the numerator. So you can see another cancellation, phi cancellation. Okay. Yeah. After cancellation and a little simplification, we have this 2 over phi minus 1. Okay, yeah. Now we feel, so this form, quite simple. Yeah, so we can start to do the, final calculation. Yeah, so let us put those two expressions together for phi cubed plus 1 over phi cubed. Yeah. That is 2 times, yeah, because minus 1 and the plus 1 cancel out. Then we take out common factor 2. So inside parenthesis, phi plus phi 1. All right. So when you see this expression, what can you get? What can you get? Because after you multiply 1 over root 5, both sides, 1 plus root 5, both sides, this expression corresponds to F3. This expression corresponds to F1, right? Yeah, F1. All right. That's exactly, we need to check, verify if this equality holds or not. That is, F3 equals 2F1, correct or not? And because we did a computation, F3 equals 2 and F1 equals 1. So this, we know this identity is correct. Okay, so that means our verification using the 2 properties of the golden ratio, we can avoid doing calculation with root 5. Yeah, because when we manipulate golden ratio symbol phi, we never need to use √5, right? Yeah, so you can see, yeah, a little easier, but a little harder, yeah, because you need to find the right way, smart way to do the transformation here. Okay, yeah, all right. I think that's pretty much enough. Yeah, yeah. Let me see if I do another verification. Yeah, verify my special case. Another one. Let me check. Fibonacci. Oh, okay. Right. All right. I'm ready. Yeah. So then it should be. Yeah. Let me go back to the slide. It should not be special cases. Yeah, because this time it should be the general. Yeah. The general cases. Yeah. The general cases. Or general case. Yeah. We treat the general situation as one case. Yeah. All right. All right. So we apply powerful tool, mathematical induction. Okay. Yeah. I just recall, we complete step 1, base case verification. And step 2, we need to make induction assumption. Yeah. All right. Yeah. So here, yeah, I just another recall. Yeah, induction assumption. Yeah. How do we make the induction assumption here? Okay. Yeah. Assume that the formula is true for k between 2 and n. Yeah. So here in this range, assumption. Yeah. So that's assumption. Okay. Yeah. All right. Why we can make that assumption? Yeah. Why? Yeah. Induction assumption. Yeah. All right. Yeah. Remember, F2 is true. We already check it, right? Yeah. F3 already true. We also check it, right? Yeah. So although we treat as redundant thing, yeah, actually, yeah, yeah, because here we can modify this range from 0 less than k less than equal to n for n greater or equal to 1. How about that? Yeah, because if we do this modification, that when n equals 1, k equals 0 or 1, so that corresponds to the base cases. Yeah. When n equals to 1, it corresponds to the base cases. We know it's correct. Okay, it's correct. All right. Yeah. That means we do not need to do F2, F3 checking. F2, F3 checking, not necessary. Okay. F2, F3 checking, not necessary for this version of induction assumption. This version. Yeah. For this version, not necessary. Okay. For this version, it is necessary. All right. Yeah. For this version, between 2 and n, it's necessary. Yeah, because if you do not check F2, If you do not check F2, then your assumption could be empty. Yeah. No such K would make it true. Could be empty. Yeah. So for this version, yeah, F2 checking necessary. Yeah. Try to follow the logic, because here we are doing some rigorous math. So you may wonder, so why we need to consider so much details? Because we want to do rigorous math, all right? Rigorous math, all right? Yeah, all right. Yeah. So that's the induction assumption, all right? Yeah. All right, yeah, here, yeah. So this formula is part of the, yeah, I need to erase a little bit. Yeah, so the Fibonacci formula, but this time I write the version, yeah. So yeah, here I write, yeah, right here, okay, yeah. All right. We write this version, okay, yeah. All right. K, yeah. So when K in this range, based on our assumption, it is correct, yeah. And this assumption is reasonable, not ridiculous, because we did the checking, okay? We did the checking, all right. But why we said that checking, I said before, the checking for F2, F3 as our practice. Practice means we do not have to do these two, yeah. In order to avoid checking F2, F3, we can change our induction assumption to this case. Then we can avoid unnecessary checking, okay? So this version, we can avoid unnecessary checking, okay? Yeah. Yeah. Yeah, because based on the original induction, mathematical induction, we only need to check the base cases. Yeah. F2, F3, they are not the base cases. So we do not have to check them. Yeah. All right. Yeah. So that it's okay. We just modify our induction assumption a little bit. Yeah. Then the last step, that's the most important step, the hardest step. Yeah. Because usually the first two steps, very easy. Yeah, we don't worry about the first two steps. The most difficult one is step 3. Yeah. We need to verify that f sub m plus 1 equals 1 over root 5 times parenthesis phi to the m plus 1 minus negative 1 to the m plus 1 over phi to the m plus 1. Yeah. Parenthesis. Yeah. Because here, yeah, before I do the verification work, let me explain a little more. Yeah, because I just guess. Yeah, because nobody give me any response. So I try to guess what you are thinking at this point. Yeah. Some of you may wonder, what's the point to do the verification here? What's the point? Because someone may argue, someone may argue, okay, argue in this way. How about making K equals M plus 1 in our mathematical induction? Now, the answer is no, you cannot do it, all right? You cannot do it. It's illegal. You cannot do it, illegal. Why? Because the reason is because out of range. For K. Only when K inside this range, you can make this assumption, okay? But now K, M plus 1, it's out of that range. How can you extend that assumption? How can you expand that range without any proof? All right? Without any rigorous mathematical work, how can you extend that range? You cannot. Okay, that's illegal. All right? Yeah. But here, we want to extend that range. We want to extend that range. But if you extend that range, you need to prove it. Prove it. Prove it. Prove that you can do it. You can do it in a legal way. The previous way, you just replace K by M minus 1. That's the illegal way. Because you didn't provide any rigorous mathematical work here, okay? And to complete that work, that is our step 3 of mathematical induction. That's the point. That's the step 3, the hardest step of the mathematical induction. So we need to do it, okay? All right, so for the remaining time today, let us do that verification, okay? Quite some work, a lot of work we need to do, okay? All right, so let's start formula transformation, okay? Yeah, pretty complicated, yeah. Let's do it, all right? Yeah. And when we start with this formula. That's legal, right? Because it is given. This recurrence regulation is given. So this step is legal, so we do not worry about it, okay? Yeah. All right. Then, first, Fn, we can use this formula. Why? Why we can use this formula? Because K equals N, this is in the range, right? Remember, what is the range? Yeah, the range between 2 and N, okay? Yeah. Actually, you can change the 2 to 0. It's fine. You can change it to the zeros, including the base cases. Yeah, it's fine. Yeah. All right. Between 0 and N, you can apply this formula by mathematical induction. Okay. All right. And the second one, you apply this formula another time, but this time K equals M minus 1, also in the range, right? So that's legal. So these two induction assumption application, both legal. Yeah, so that's correct. Okay, all right. Then our goal, what is our goal? Okay, what is our goal? Our goal Yeah, so here we do simplification. Yeah, these two, I just factor out a common factor 1√5 and put all the four terms inside one big parenthesis. Yeah. All right. Yeah. All right. Here, yeah, the goal, yeah, before I do further, the goal we want to verify, because remember, our goal is the right-hand side equals replace K, extend the range, right? Replace K by n+1, but we know that replacement should be proved. All right, yeah. So we need to prove the left-hand side expression exactly equals, the right-hand side, this whole thing exactly equals this left-hand side expression. We need to prove it. Okay, we need to prove it. All right, yeah, prove it. Oh, sorry, minus, not plus. Yeah, because I write it here. Okay, we need to prove it. All right, yeah. To prove it, let's compare. Yeah, because 1/√5, that's the same 1/√5. So we can ignore 1/√5. We just compare that big parenthesis. Yeah, everything inside that big pair of parentheses. Yeah. Then the integral terms, they have the same type of structure, right? The power function or polynomial function. You can call polynomial function. Yeah, that kind of structure. And the fractional part and the fractional part they have the similar structure, right? So they should match. Integral part, they should match. So we can make our reasonable guess. We want to verify the integral part should match. That means this equality. The fractional part should match. That means this equality. How about that? Yeah. So here, these two just our guess, okay? Yeah. If you ask me why they are true, we need to verify it. Yeah. Here in our mind, before we do verification, we need to know what we are going to do. Otherwise, we do not have the direction to go. Yeah. So this guess is our direction to go. Okay. Yeah. All right. But we need to answer why the first one is correct, why the second one also correct. Okay, yeah. If we can answer these two questions, then we complete the whole verification. All right, yeah, all right, yeah. To do that, we start with our property number 2. Remember in the previous slide, we have 2 properties for the golden ratio. Yeah. This is the second one. Second property. Okay. Phi squared equals phi plus 1. Yeah. Now let's work on this property. Yeah. It's correct. Okay. Yeah. So we start from this correct equality. Yeah. Then we multiply some power of phi, yeah, the same power of phi, both sides of this equality. Yeah. When we multiply what power of phi, we can get phi to the n plus 1. Okay, that is, you can see that is phi to the n minus 1. Phi to the n minus 1. If we multiply that power of phi we can get phi to the n plus 1. But at the same time, right-hand side, we also need to multiply phi to the n minus 1. So the first term becomes phi to the n. The second term becomes phi to the n minus 1. Yeah. That's exactly matches what we guessed before. Okay? Yeah. That means our guess is correct. Yeah. So this is a proof. Yeah. This is the proof. Okay? Yeah. All right. How about our second guess? We need to verify it, right? Yeah. So the first guess is correct. The first one is verified. All right. The second one, how to verify this one? Okay. Yeah. So this time, we need to use the backward thinking. Yeah. Because it is a little more complicated than the first equality. The second equality, more complicated. So we want to make the second equality as simple as possible. Then we can apply some property of the golden ratio to verify it. Yeah. So before we transform this relatively more complicated form, it's hard to apply our golden ratio properties directly. So for that reason, so we do backward thinking to make this form simpler. Okay, all right. Yeah. First, can we remove that negative one part? Negative one part, quite annoying. Yeah, we feel, if we attach some power of negative one, it's quite annoying. Okay, can we eliminate the negative one part in this formula expression? Yeah. All right. Yeah. So, first, I removed the denominator part by multiply common denominator. So, yeah, the common denominator phi to the n plus 1, common denominator, right? Common denominator, okay, you multiply both sides of that equality to be, because we need to verify it. We use backward thinking, all right? Yeah. So the first round simplification, so we treat this as the first round simplification. We remove the denominator part by multiplying appropriate common denominator. The second simplification step, we try to remove the negative one annoying term, or form. Yeah. So how to remove that? Let us multiply negative 1 to the n minus 1 both sides of this form. So we get 1 equals phi squared minus phi. Yeah. Can you see that? Okay. Can you see that? Left-hand side, because it would become negative 1 to the 2n. That's 1, right? 2n is an even number, so that's 1. Then, for corresponding to the first term at the right-hand side, negative 1 to the 2n minus 1, that's an odd number. Okay? Oh, sorry. Yeah. Yeah, because, this one, phi, yeah, because that one corresponds to phi. So that is an odd number, negative. So that means the sign for phi is negative. The sign for second one -1 to the 2n minus 2, another even number, right? But this is for phi squared, so that's positive. That is for the square term. Yeah, so that is the simplification. So you can see, yeah, after we do 2 rounds simplification, we get this form, but this is the first property of golden ratio, right? The first property, 1 equals phi squared minus phi, and then we know it's correct. Okay, so we check it. Correct. Then by backward thinking, then our, previous equalities all holds by backward think, by equivalence of our formula transformation. Okay, equivalence of our formula transformation. So all correct. Okay, so then that means the whole verification is correct. The whole verification is correct. So we complete mathematical induction procedure here. Yeah, we completed. That's the whole story. Okay, although a little complicated. Yeah. So think about if you can follow the whole proof. Yeah. If you can understand all the details in our proof. Okay, try your best to understand. Yeah. Here, for this class, just let you know, you are not required to apply mathematical induction to do any proof for this class. Okay, yeah, I do not give you any such problem because it could be too hard for you. Yeah, but at least I give you one such question in my lecture to let you see what is the complete procedure by applying mathematical induction to prove some, to verify or prove. Yeah, so you can use, both ways. Some result you feel it's correct. Okay, yeah, all right. So I just show you once. Yeah, and you need to try your best to understand this procedure. Yeah, because if in future in your real world applications you may have the similar situation, then you should do in this way. Okay, yeah, just let you know. Yeah. When you guess something, yeah, think about this. If you guess some formula, but you do not know if it's correct or not, yeah, you can do some experiments for the verification, but experiments cannot be treated as a proof, right? Yeah. So experiment just give you more confidence. So your guess is correct. In order to prove your guess is really correct, then you need to do some rigorous proof work like this one here. Okay, that's the point I want to convey here today. All right, yeah. Otherwise, other than that, you do not need to worry about if you need to write a rigorous proof like the one here. No, yeah. For this class, I do not require that. Okay, all right, yeah. So the verification is done. The last subtopic for this part E, discovery. Yeah, because at the beginning I mentioned the Fibonacci formula, is a magic formula. Yeah. Because if someone can guess that, then the only way we can understand, that's by magic. Because no reasonable person can make that good guess, right? How can a person can relate Fibonacci numbers to golden ratio related formulas? And nobody can do that. Yeah, so that's why I use magic. But actually, it's not magic. Okay, it's not magic. So, but in order to understand, there is some reasonable way to discover that formula. So we need to do this part E.3 to provide you the, reasonable procedure for discovery. Okay, yeah. Discovery, okay. Yeah, that's important. Yeah. All right. So the topic we call the linear recurrence relations. Yeah. Or solving linear recurrence related or equations. Yeah. Replaced by equations. Yeah. And this part, the topic of this part, actually, you already learned it in discrete math. Discrete math. Okay, yeah. Some of you may still, you can remember a little bit, yeah. Some of you, may not feel comfortable for this topic, yeah. So the next time I will go through all the details of this part next time. Yeah, today, because I do not have that much time, yeah. I need approximately 20 minutes to complete this part, E.3, 20 minutes, okay? Yeah, and I do not want to skip this part, yeah, because I like to assign you some questions in this part, in your homework, yeah, linear recurrence relation, yeah. And this part, so you learn in discrete math, and here, I like you to learn this technique another time, because if you know how to discover this kind of formulas, that would be very useful for you, okay? So for that reason, I require this part, okay? Solving linear recurrence relations or equations, we will do next time, yeah. After that, in our homework assignment number 1, I will give you soon, you will see, I will put the last question, solving this kind of linear recurrence relation, okay? All right, so let me stop right here today.